Hi, welcome to the course Data Science by Route Fabric. In the previous lessons, we learned about supervised learning and we briefly touched on linear regression and logistic regression. Now let us see what regression really means. Regression analysis is a form of predictive modeling technique which investigates the relationship between a dependent and independent variable. A regression analysis involves graphing a line over a set of data points that most closely fit the data. There are a couple of uses of regression. Regression can be used to determine the strength of the predictors. It can be used to forecast the future events or future effects of a trend. It can also be used to see the trend forecasting for climate or stocks. Now let us see the difference between linear regression and logistic regression. The core concept of linear regression is that the data is modeled using a straight line, whereas for logistic regression, the probability of some obtained events is represented as a linear function of a combination of predictor variables. Nextly, for linear regression, we use continuous variables, whereas in a logistic regression, we use categorical variables. The output of a linear variable is the value of the variable, which is a continuous variable number, whereas for a logistic regression, it is a label or a categorical variable that is given as the output. To decide the accuracy and the goodness of the fit of a linear regression, we use the loss function or the R squared, whereas in a logistic regression, we use the accuracy, precision, confusion matrix, and F1 score. Now, where is linear regression used? Linear regression is used to evaluate trends and sales estimates. It is also used to analyze the impact of price changes. If we change the price of a banana, are people going to buy it at the same rate? Or if we change the price of apple, will people buy more bananas? It can also be used to assess the risk in financial services and insurance domains. Linear regression model is actually very simple. It is just the normal formula that we use, y is equal to beta plus beta 1 times x, where betas are the bias or the intercepts of the function. The beta naught and beta 1 are found by using the data. There are a couple of models in linear regression. There is simple linear regression, ordinary least squares for multivariate linear regression, gradient descent, and regularization methods to help with linear regression models. A simple linear regression only has a single input. Usually these type of models we can estimate with using general statistics. When there is multivariate involved in the problem, that is when we need to use something more complex, like ordinary least squares. The ordinary least square procedure seeks to minimize the sum of squared residuals or squared errors. This means that given a regression line through the data, we calculate the distance from each point to the regression line, squared, and sum all the squared errors together. This is the quantity that ordinary least square seeks to minimize. The lower the least square, the better the model functions. This approach treats the data as a matrix and uses linear algebra operations to estimate the optimal values for the coefficients. It means that all of the data must be available and you must have enough memory to fit the data and perform matrix operations. Next up, we have gradient descent. Gradient descent is probably one of the most popular models in machine learning. We'll be using gradient descent even in neural networks. When there are one or more inputs, you can use the process of optimizing the values of the coefficients by iteratively minimizing the error of the model on your training data. This operation or this process is called gradient descent. This works by starting with random values for each coefficient or random weights. The sum of squared errors are calculated for each pair of input and output values. A learning rate is used to scale factor and the coefficients are updated in direction towards minimizing the errors. The process is repeated until a minimum sum squared error is achieved, or a local minimum or a global minimum error is achieved. When using this method, you must select a learning rate, which is the alpha parameter that determines the size of improvement steps to take on each iteration of the procedure. The lower the alpha rate, the more processing time it takes for your model to compute. The higher the alpha rate, the faster your model is going to compute, but the accuracy might be low. If the learning rate is too low, there is a chance of going into overfitting or being stuck at a local minimum. Now let us look at regularization. Regularization has two methods, or two types. One is the lasso regression, which is L1 regularization, where ordinary least square is modified to also minimize the absolute sum of the coefficients. Whereas we have ridge regression, or L2 regression, where ordinary least square is modified to also minimize the squared absolute sum of the coefficients. If we use L1 and L2 regression, which is lasso regression and rigid regression, we call it an elastic regression or elastic regularization, where both the concepts are used and the balances are set based on the machine learning model and how the data reacts. Now let us see how predictions are made with linear regression. We already saw the formula of y is equal to beta naught plus beta 1 times x. For multivariate linear regression, we have y is equal to beta naught plus beta 1 x plus beta 2 x2 plus and so on till the end. We also have an error function at the end in the multivariate to balance the weights. In simple linear regression, all we need to do is use the y values and the x values from the dataset and find the bias or the intercepts beta naught and beta 1. Similarly, in the multivariate, we find all the betas. After we have all the betas, we can use fresh data, which is the input data, which is x values, to find the new y values. Now let us look at some data pre-processing methods that can help yield better results for linear regression. First, we need to assume linearity. You may need to transform data to make the relationship linear, that is, use log transformation for an exponential relationship. Nextly, we need to remove noise. Any kind of bad data or impurities in the data is going to affect the accuracy of your model. To have the best accuracy, you have to remove the noise. Be careful while removing the noise because you might remove more data and you might cause overfitting and affect the data. Next up, we need to remove collinearity, and we need to, if we can, convert the distribution into Gaussian to make it a more reliable prediction. We should also normalize the inputs, which is normalization and standardization of the information, so that it is easy to process and it is a normal distribution. I hope this was informative. To learn more about data science and machine learning, please visit robfabric.com. Thank you and have a nice day.